Let's take a look at some of these practice problems that we have on this math practice. That would be a good thing. So we're going to start off fairly straightforward here. You can see we've got this one with the car. For all these problems, we're going to begin with a velocity time graph. So let's start there so we can get an idea of what we're looking for. Car traveling in a straight line has a velocity of, okay, this right here is going to tell me my initial velocity, right? That's my initial velocity. There's the amount of time that's going to elapse. I should be starting at a time of 0. And then as you can see here, I have a velocity of 8 meters per second. So that's going to be my final velocity. And I'm looking, as you can tell, for my acceleration during the time interval. So with that in mind, notice I'm not going to start at the origin. I'm going to start somewhere above the origin, and I am getting faster. I'm going from 5 to 8. So I'm going up at some point. So 5 meters per second. Right, this is in meters per second, and here I'm going to be at 8 meters per second. And I am looking for the average acceleration. Oh, wait, I forgot the time. The time is here. Let's say we're here, so that's going to be at 4 seconds. So there's my time final. I'm looking for the average acceleration, which tells me I'm looking for the slope of the line. So as we know, the slope of the line is going to be the rise over the run. So VF minus VI, TF minus TI. As is often the case, my initial time is 0, so away it goes. I'm going to take my 8 minus 5 meters per second divided by my total time elapsed, which is 4 seconds. So we're going to end up with 3 over 4. But we don't like fractions in physics class. We like decimals. So 0.75 meters per second squared. Now this question doesn't ask, but if you were asked how far the car travels in this length of time, keep in mind what you would be looking for would be the area under the curve. And in this case, it is not a triangle or a rectangle. It's a trapezoid. But you can break it up into a triangle and a rectangle, and you could add them together if you wanted to know how far the car went. All right, so there's our first one. Hopefully that was an easy one for you. Now we're going to move into one that's a little trickier. So you toss a ball straight up into the air, and you're going to catch it at the same height, and you've got a total time, and you're looking for the altitude. How high does it go? Okay, so first again, let's start with a graph. This is one of our special scenarios where you have to remember that you're going to be starting in the first quadrant. You will have some sort of an initial velocity when you toss the ball, because if your velocity was 0, it would never leave your hand, right? So it's going to go up in the air. It's going to go, I mean, let's face it, what is it going to look like? You're going to go like that, right? That's the position time graph, really. That's what it would look like if you were doing an xt graph instead of a vt graph. So from here to here, the ball is slowing down, right? And here is where the ball stops. So how does that look on a velocity graph? Well, it is slowing down, so it's approaching the 0 line here. That's where the velocity is 0. And then it comes back down and it gets faster. So you're going to keep on going. This is, I kind of called this, it was bow ties, right? It looks like a little sideways bow tie here. All right, my slope of the line is negative 9.81 meters per second squared, because that's my acceleration due to gravity. Even though they don't tell me that, it's assumed that you know this. Okay, so what else do they tell us in the question? It takes 5.6 seconds from where you toss the ball up in the air. Okay, so that means your total time in the air, all the way to here, that's your 5.6 seconds. Now, if you go and you land on the same spot that you started, one of the nice things is we can split that right in half. And so there's the time up and the time down, and they should match if you land at the same spot. So you should be able to tell me what the time is at that point. In this case, if you cut that time in half, it's 2.8 seconds. All right, you also should know that your velocity at that point is 0, because it's crossing the x-axis. So this question is asking, how high did it go? So what you're being asked to find is the altitude, and that equates to the area under the curve. These two are identical, this one and this one, but the truth is you only need this one, and you should be able to answer the question. Okay, so I'm going to work again with my area under the curve as well as my acceleration. I often start with the acceleration. just because, well, it's habit. I always start with the acceleration. Let's see what we know. Negative 9.81 meters per second squared for this guy. And then let's think about this. We're gonna focus in here on this point. We're gonna make that a natural midpoint here. So my VF is gonna cancel out. My TI is 0 as well. So I'm going to have negative VI, and my TF is going to be 2.8 seconds, which is nice because now I have 2 out of the 3 variables, right? So that makes it really easy. I'm just going to multiply both sides by 2.8 seconds, right? And I will know VI. So negative 27.5 meters per second equals negative VI. Well, let's divide that by negative 1, shall we, and get it out of there. So there's my initial velocity for the ball right there, 27.5. Now, that's not the answer I'm looking for. That's only my initial speed when it leaves my hand, which is ridiculously fast. So, I mean, the major league should be calling you for that one. But in any case, made up numbers, what can I say? You want to know this area under the curve. So let's got a triangle here. We know that's 1/2 base times height. And keep in mind, the base here is going to be the time, right? We're going to go from 0 to time final, which is right here. So that's going to be my 2.8 seconds. My height is going to be to VI, and I know my VI now is 27.5 meters per second. So I actually have the pieces of my triangle, which makes it very, very handy. So again, the base, 2.8 seconds, the height, 27.5 meters per second. And when I do the math, I'm going to figure out that that is 38.5 meters. There's my second question. All right, hopefully so far so good, right? Remember, you can always pause and rewind and go back and try it again if you absolutely need to. Okay, so this next question is kind of a different one, right? Again, it says that this guy, he's a pitcher for the Cleveland Indians, gives you his initial velocity for his pitch is 44.1 meters per second. And you want to know, what if he'd just thrown it straight up in the air? How high would it go? All right, so some of the key things here, right? It's always good to be able to decipher the questions. That's going to be my initial velocity. And if he throws it straight up, how high would it have gone? Well, you know, at the peak of flight, the velocity is going to be 0, right? And we are really trying to figure out delta x. We're trying to figure out how high it honestly goes. So again, this velocity time graph is going to look very much like the last question, right? We're starting here, and it's going to go to the peak of flight and then turn around and come back. And again, we want to know how high it goes. Okay, I'm going to see if I can catch those as they come in and stop the recording so we don't have to hear the announcements on the tape. That's not very helpful. All right, so 44.1 meters per second would be here. That's my initial velocity. My final velocity would be 0. All right, so my final velocity is going to be 0 here. I do not know how much time this is going to take. I probably should figure that out, but I do know that the slope of my line, again, is gravity, right? The ball is falling. So let's start with our acceleration. Slope of the line. What are we going to cancel out? VF, because VF is going to go away. TI is going to go away. So negative 9.81 meters per second equals negative 44.1 meters per second over TF. We can very quickly figure out the time that it's going to take for the ball to reach the peak of flight. The biggest problem you're going to have is not making an algebra mistake, because that's what I usually see, especially when your missing variable is on the bottom of your fraction. So keep that in mind. We're going to multiply both sides by TF to get it out of the bottom. And I'll start working back over here. Negative 9.81 TF equals negative 44.1 meters per second. Okay, so if we divide to get TF by itself, now we're going to know what TF is. And 4.5. Now that we know that, right, that makes this 4.5 right here. We should be able to do the area of that triangle, and we will know how high the ball goes. All All right, so delta x equals 1/2 base height. 1/2 the base is 4.5 seconds. The height is 44.1 meters per second. And then when I do the algebra, I get 99.1 meters, give or take. All right, another one being tossed up in the air. Okay, next question. Okay, you know what? This is the toughest question, so I'm going to go to the next one. Let's try that. They're both kind of tough, but we'll give this one a try first. All right, let's go here. Number 10. This one's a little bit different because the ball is being... Now, you know what? Come to think of it, I'm going to change my mind again, because why not? Why not? And the reason I'm going to change my mind again is because it's another ball getting tossed up in the air, and we seem to be on a theme here with that. So let's take some time and do that one. So you are on a building. Let's go back. You're on a building, 75 meters tall. Toss the ball straight up. How high does it travel? And then it goes up and comes down. How much time is in the air? You know what? I'm going to actually start with a diagram on this one. I'll put it down here, though. All right, so it's saying I toss the ball up. I'm on this building. I toss the ball up, and then the ball goes all the way down to the ground. So this is a new type of problem for us. So from here to here, 75 meters. So the ball is actually going to travel to the peak of flight, and then it's going to turn around. It's stopping here, and then it's going to travel all the way down here to the bottom. Okay? Now, these two values right here, that distance, those are the same, of course. And of course, these two are the same. So this is 75 meters over here. If I figure out how high the ball can go, like, I don't know, let's make up a number. Let's say that number was 100. Not very much to scale, but if it was 100 meters into up this way, like this, that means that this value here would also be 100. And I'd add it to the 75 and get 175. Make sense? I hope so. All right, let's draw a VT graph. What is this going to look like on a VT graph? Well, I want my VT graph to have a little bit of space here. And I might, I'm going to have to definitely make sure I have enough room for this one. Okay, so I start by throwing the ball up into the air. It slows down, it stops, it turns around, and then it goes. It goes for a while. So what you effectively are going to see here is that my second triangle is much larger than my first triangle. That's kind of critical, okay? And I know that whatever this value is in my first triangle, well, actually, let me rewrite that so it makes better sense. All right, I'll fix that a little bit there. Okay, so this is going to go down 75 meters, right? I'm going down 75 meters here. That's why I'm going to put a negative 75 because I'm going down. Plus whatever the value is of the first triangle. That's going to be the area of my second triangle. At this point, I am still going to have a velocity of 0. And obviously, I'm going to have some value for t up until that point right there. The slope of my line all the way through is still going to be gravity. So far, I mean, the big difference here is that second triangle. But I haven't done anything much with it yet. Okay, so let's start with the first triangle, because I can work with that. All right, now let's also consider what other things I have not written down. It tells me here that my initial velocity is 33.8. So that gives me another point on my graph, which is awesome. All right, so let's figure some stuff out. I'm going to change colors just to break this up a little bit. Let's go with blue. All right, so I'm going to start in this little space over here. Let's start with acceleration equals Vf minus Vi, Tf minus Ti. But I'm going to focus on the top. That's where I'm going to go first. Okay, so negative 9.81 equals, now my Vf is 0, my Ti is 0. So negative 33.8. So far this is looking a lot like the other question over Tf. And oh look, I can figure out my time. Right? I'm only missing one thing. Let's get Tf out of the bottom. So when I do the math here, where is it? 3.45. Okay, so 3.45 seconds from here to here. Now, considering I know that this is 33.8, I can figure out the value of that first triangle. And so I'm going to kind of squish this over here in the corner. So I'm going to take 3.45 because that's my base. I'm going to take 33.8 meters per second because that's my height. And I'm going to do that math, and I'm going to get 58.3 meters. What that means is that this isn't really a 1. This is a 58.3 meters, right? Because that's how much this is. That's how high up it's going to go from here to here. This is 58.3 meters. Now, I know it's got to drop 58.3 meters and then another 75 to hit the ground, which is why I'm doing this, right? So if I add that together, I get 133.3 meters. So the area of this big giant triangle is actually, and it is in the fourth quadrant, so it should be negative, right? So we're going to have negative 133.3 meters. Now, the question, though, is saying, how high does the ball travel? Okay, so that's the first part. We got it. 58.3, answer to my first question. It goes up and falls to the ground below. How much time is it in the air? All right, so we know how much time it takes to go up, right? Now, I could argue that if it takes 3.5 seconds to get 4 or 5 seconds to get here, it's going to take 3.45 seconds to get here. And then I could figure out the time to go down. And you would not be wrong if you argued that. But I'm going to tell you, your math is going to be difficult. There is an easier way to do it. And the easier way is to go from the peak of flight to the ground, to start it here and then figure out this. Now, you can do this one of two ways. One is an easier way to do the math, and one is a more difficult way to do the math. And I know you want the easy way to do the math, so I'm going to show you that one. Here is my trick. Here's my trick, and I'm going to write it in red. We're going to say to restart the clock right there. Restart the clock to time 0. Figure out this from 0 to TF again. All right, here's why. If you go from the origin and you say TF minus 3.45 is going to be the difference, you are correct. You are going to end up doing the quadratic equation. And I know how much everybody loves doing the quadratic equation. No, you don't. Let's skip the quadratic, shall we? Let's keep it simple. Okay, so this is my trick for you when you have two triangles that are not the same size. Restart the clock to 0 here. And let's do this again. We're going to use the same techniques, but we're going to use some different values here. Okay, now remember, this V is not negative 33.8. It's dropping much, much further. It's going to be going much, much faster by the time it hits the ground. So VF, I have no idea. All right, so we're going to probably end up with a system of equations again, but this is not the worst thing ever. We can totally do this. Not a problem at all. Okay, and we want to know the time in the air anyway, so once we use the system, we usually find TF in the first place. This won't take us all that long. Let's start with acceleration, VF minus VI, TF minus TI. Okay, we're resetting the time to 0. And the initial velocity from this point will be 0 as well. So negative 9.81 times TF equals VF. I kind of hop-skipped 2 steps in there, all right? I put my 9.81 and I moved my TF over. That's going to help me there. Let's do my delta X. Let's do my area. All right, so 1/2. My base, there it is. It's TF. My height is here. It's going to be VF. I don't know either one of those, but I do know the area of my triangle. It's 133.3 equals 1/2. Now, I'm going to take this and I'm going to put it right there. I'm going to substitute it in. So we've seen this before. This is not new to us. 9.81 TF. Now, it's completely up to you whether you want to move the 2 over or you want to multiply the 1/2 across. I am going to multiply the 1/2 across in this case, so negative 4.9 TF squared divide both sides by 4.9. Don't take a square root at this point. I saw somebody do this on the quiz and they just took a square root of both sides and I'm like, oh my God, no, 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 no. Order of operations, do your division first, okay? And so what you're going to get here then is TF squared equals, now remember your negatives are going to cancel out, so you're going to get 27.18. When you take the square root of this, you'll get 5.21 seconds. Now, keep in mind, that is only from here to here. You still have to add the two together to get the total time in the air, but oh my gosh, that was so easy, right? So we're going to say 3.45 seconds plus 5.21 seconds. My final answer is 8.66 seconds. There it is. That's the new tricky dropping one where it does not match. One side of the triangle does not match the other. Okay, rewind that and go back if you have to. All right, but this is the key to keeping the math doable. Otherwise, you're going to end up with a quadratic equation, which is always fun. I mean, you're welcome to solve one. Go right ahead. I just don't want to do it. I always have to use a computer to help me with that because I don't like to memorize that and write the whole thing out. What a pain in the tuchus that is. Okay, so our very, very last one here, number 10, the ball being thrown straight down from a bridge with an initial velocity of 18.5. We're given the time in the air. How high is the bridge? Our graph is going to look a little different right now. All right, so that's why I changed my mind on this one about going back and doing the other one. All right, so the ball is being thrown straight down with an initial velocity of 18.5 meters per second. Well, you know what? If it's being thrown straight down, that's not really 18.5. It's negative 18.5 meters per second because it's downward. Yes? All right, and here's my time, of course, and I want to know how high is the bridge, so that's delta x. Okay, so if my initial velocity is negative 18.5, that means it's starting like down there. I mean, I don't know, wherever, but it's down in the fourth quadrant. And yeah, gravity is going to accelerate it after that. So we still have negative 9.81 meters per second squared. That doesn't change. All right, and we know that the time it travels is 2.3 seconds. Okay, that helps me, so I can make my little triangle here. I want to know how high the bridge is. That's kind of the key. All right. And oh, wait, I got to label this part. I forgot. Let's do that. Okay, so I have a decent amount to work with here. What I do need to know, I need to know the final velocity down here. So let's start with that, shall we? All right, as usual, let's start with acceleration. Acceleration equals the slope of the line. The slope of the line is rise over run. There we go. Negative 9.81 over here. My final velocity is what I am looking for. My initial velocity is not 0. And I have to watch out for this extra negative in here, don't I? Because I have 2 of them. Don't leave one out. You don't want to do that. 2.3 seconds, right? Because TI, we start at time 0. We've got 2.3 seconds right here. Okay, so I'm running out of room, so let's go to the top. Negative 9.81 equals VF plus 18.5 over 2.3 seconds. All right, before we get crazy with the math, let's get rid of the fraction. That always helps if we get rid of the fraction. So multiply both sides by 2.3. Yes? Okay, so what I end up with then is negative 22.563 equals VF plus 18.5. Okay, I want VF by itself. Subtract 18.5. A little different than what we're used to, but it's not terrifically difficult math. You just have to make sure you do the algebra in the right order. The right order of operations is important. Okay, so I know now that this is going to be negative 41.06 meters per second down there. I still want to know how high is the bridge. This is where the graph becomes critical. Excuse me. This is not a triangle, guys. Right? I started here. That's a triangle, but I also have the rectangle. I need them both. I need them both. Okay, so if I want to know delta x, I need these both. Now, let's start with the rectangle. The rectangle is easy. That's length times width. So the length of the rectangle here is 2.3 seconds. The width of my rectangle is negative 18.5 meters per second. All right, so I'm going to begin with that. And then actually, because I didn't bring a calculator over and I did this whole thing in one single step on my answer key, I'm going to just hang on a minute. All right, so of course that's going to equal the delta x of number 1. The delta x of number 2 is going to be, let me pick a final color here, we'll pick green. It's going to be this triangle, right, and I got to do that one. So delta x2, that's going to be 1/2 base times height. The base is still 2.3. The height from here to here is going to be the 41.06 minus the 18, what did I say, 18.5. All right, I have to subtract those two. Minus the 18.5. And honestly, I think I just messed up the negatives there. So let's try that again. Let's try that again. You get the idea, right? I hope. I hope you get the idea of what I'm doing. Okay, because I got to start here, and that's where my negative 18.5 is. So I'm going to have my negative 41.6 minus my minus 18.5. When I do that math, when I actually use that in the calculator, I'm going to get negative 22.56 meters per second. You can check my work. Okay, when I take these two, this one plus this one, and I figure all of that wonderful math out, what I'm going to get is negative 68.49 meters. That, now, the way this question is phrased, how high is the bridge? This is how far the ball drops, or the whatever it is, yeah, a ball. This is how high the bridge is. We would actually make it positive if we want to know how high the bridge is. Okay, so I am hoping that these 5 questions can kind of help you, not just with the math, but also with drawing the graphs, seeing how the graphs fit together. We've got a little time until your test. Please, please, please practice. Come see me for some help if you can't figure these out. All right, I do want to help you, but I need to be able to have a conversation where you've already done some work and you know where you're stuck. It's so much more productive, everyone. All right, so I hope this helped, and I will see you in class.